Now, if we go to multiple regression, that's where a lot of our model fitting is going to happen. Multiple regression, the idea there is simply that instead of trying to fit y equal mx plus b, I'm going to try to fit something like in a lot of things will say something like, beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus, and these aren't data points x1, x2, these are variables x1, x2, x3, up to some m, beta m, xm, and then plus an intercept, so to speak, of x. So this is an m-dimensional problem. If I just had something like y equal beta 1 x1 plus beta 2 x2 plus alpha, all right, well then, we're talking about, we've got points out here in space and so forth, and we're maybe trying to find a plane in space that will fit this, and so this is a plane in three-dimensional space, two-dimensional plane in three-dimensional space, and so that's what we're trying to fit. And well, it's pretty much the same mathematics. You could do it using multivariate calculus, you could do it using linear algebra. It's all the same. And in this case, when it spits out the values, you'll get a you'll get a beta 1 hat, and you'll get a standard error for that beta 1, and you'll get a beta 2 hat, and you get a standard error for the beta 2. Okay, and you'll all and same thing all the way to alpha, the intercept, and you'll also get an r squared. Okay, so that again will tell you the percentage explained by the model, that r squared. So percent explained, percent of, I didn't say percent of what, percent of the variation in y, explained by the model. Okay, so that's all multiple regression is doing, but it turns out that gives us a great tool, and the way we can use this is, you see that suppose I would like to fit something that looks like this, something like a2x squared plus a1x plus a0 with my data. So I want to fit a quadratic, right? I've got data that look like that. Well, that looks like a quadratic to me, so I would love to fit that with a quadratic. Well, it turns out that the mathematics of the multiple regression, it doesn't care where you got your data. Just give it the data. So for instance, what I might have here is, I'd have an x and a y, and here's 3, 4, 6, 7, 8, 9, right? Why'd 5 and 6 run away? 7, 8, 9. And so you have this, but you see what we can tell the multiple regression is, oh, we would like you to fit, and I'll go back to the betas, a beta 2 x2 and a beta 1 x1 and plus an alpha. But what we don't tell it, and it doesn't care, is that our x1 is x, and so that's 3, 4, 6. And our x2 is actually x squared, which we'll calculate and put in 9, 16, and 36. And then our y values are 7, 8, and 9. But you see, it doesn't care, and so we just give this to the multiple regression. It will calculate beta 1 and beta 2, and if it and alpha, and if it found that alpha was 3 and beta 1 was -1 and beta 2 was 2, then we would have y equals 2x squared minus x plus 3 as our model of best fit. So pretty awesome the way we can use multiple regression to fit any general linear model. Okay, and by general means if we can do a variable substitution, something like this, that makes it look like a linear multiple regression, hey, we're all set. We can do that. And now it could be just a simple regression because of the transformations you make. But in the end, if we can do that transformation, then we can just use the multiple regression to get our coefficients, our parameters, and move ahead. We won't, there are statistical concerns if you're trying to do tests of hypotheses and all that, but we're not going to get into those. So we're just, mostly interested in trying to use these tools to fit our data. We want to learn a little bit enough about it, things like the standard error and confidence intervals and the R-squared, to help us do a better job of fitting models. But we don't need to get into it so greatly that we're spending all our time on the statistical theory of general linear models. But so that's the beginnings of multiple regression. We'll do more with some of the transformations and more with R-squared and adjusted R-squared and what we mean by that. Okay, so we'll call that one done.